I'm delighted to introduce Andrew Detor from GE Research. He is a senior principal scientist at GE Research in New York and New York State. And he will tell us today about a material informatics approach to refractory high entropy alloy development. Andy, with that, the stage is yours.
Okay. Thank you for the introduction. Thank you everyone who's listening in here. I'm excited to share with you all some progress we made recently on a DARPA-funded program looking at refractory high entropy alloys and how we can develop new compositions to overcome some limitations in the area. And I'd like to start with a little bit of background on refractory alloys, and what some of the constraints are and what some of the challenges are that we're trying to address here. So Noah Phillips wrote an excellent article last year, sort of summarizing the past 50 years or so of development effort in refractory alloys. And the conclusion out of the paper was really that there's been little progress made since the 50s and 60s. And the alloys that we're using today commercially, alloys like C103 and TZM, have been around for a long, long time. And the challenge with refractory alloys is balancing a number of competing properties: oxidation resistance, strength at temperature, and fabricability. And this has been a challenge for a long time, and we have to make choices and trade-offs. So the alloys we use today, C103 and TZM, are excellent high temperature materials. They can be produced, but they really lack oxidation resistance, and they don't really have exceptional strength at the highest of temperatures. So the question that we asked on this recent program is, what can refractory high entropy alloys do to potentially solve this problem? And just to explain very, very briefly, high entropy alloys, for those who haven't heard the term before, are complex mixtures of elements where instead of having a base, like C103 has a niobium base, TZM has a molybdenum base, you're free to include the elements really in any proportions that you'd like. It can be an equiatomic alloy. It can have concentrated combinations of more than one element. And what that does, physically, it can unlock some new mechanisms that we're still, as a field, learning and trying to understand. So the question is, can refractory high entropy alloys help us better balance properties for these really aggressive applications where these alloys are used? The approach that we took on the program was really to open up the book, right? Open up the palette of possible elements to the ones you see listed on the slide here. So we include the normal refractory block plus rhenium and ruthenium. And in general, if you do the literature review, you'll find that if you sort of move to the upper left-hand side of this block, you tend to get alloys that are better in oxidation resistance and ductility. Moving to the lower right, you tend to get alloys that have better high temperature strength. And so what we wanted to do was explore this, but not explore it like they did in the 1950s and 60s, but explore it with a modern tool set. So we're bringing into this project really the four things that you see listed there: high throughput experiments, which I'll touch on in the next slide, exactly what we're doing; CalFAD thermodynamic modeling to predict phases using off-the-shelf product, ThermoCalc; machine learning to try to interpret and understand the complex trends that are coming out of the experiments. And then with those machine learning surrogate models, we can run a true multi-objective optimization process to find that best balance of properties. And we're not putting any constraints here on composition. We are free to explore this entire palette. And so the notion here and the nuance is that we're not running a traditional alloy development program where we use sort of precise established test protocols, trying to get accuracy to the third decimal point. Here we're running high throughput. So the intent is so-called direction, not perfection. We're trying to get to our destination as fast as possible using these combination of tools and approaches. So I want to talk briefly about the experiments that we ran, just to give you a little bit of context for the analysis and data that will follow. We're running experiments. So these are not computational models. This is ground truth data